So now that we've talked quite a bit about some of the fundamental chemical reactions that occur in the stratosphere here in chapter 1, we now move into chapter 2 where we do a deeper dive into the chemistry of ozone depletion. And the reason we do this is because this phenomenon, this atmospheric phenomenon of ozone holes, is really kind of a very important topic when we talk about atmospheric chemistry. So you might wonder, what exactly are ozone holes? Where are they located? What causes them to some degree? And some of this may be familiar chemistry and some of it may not. But you might wonder, where did they really come from? So let's dive into this just for a moment. Now, the chemistry of ozone and ozone measurements have been made all the way going back to the early 1900s. The Chapman cycle that we talked about in chapter 1, that was actually proposed and published in 1930. So there's been a number of investigations into stratospheric chemistry for a long time, and particularly in the Antarctic region, so near the South Pole, in the 1950s, the British Antarctic Survey was making measurements, and they started to notice from the 1950s onwards that the levels of ozone would decrease at particular times during the year, kind of annually, and those decreases seem to be more significant as time went by. And so if we just look here at a few years going back to 1979, and here we've got a depiction of the South Pole, you'll notice, although you may not fully understand what it is at first, we see that there's some clear phenomenon going on. In 1994, we have this large blue circle around the South Pole. And then that seems to have decreased a little bit by the time we get to 2019, that's last year, but certainly not quite as small as we were back in 1979. So this is just a graphical representation of the concentration of ozone over that region. And it's listed in a unit known as the Dobson unit. Now, what exactly is a Dobson unit? We use this specifically for ozone. And 1 Dobson unit is equal to 0.01 millimeters of pure ozone at standard temperature and pressure. So essentially what that means is that if I have a column of air up through the atmosphere, and I said that there were, let's say, 200 Dobson units of ozone in there, that would mean that if I took all of the ozone in there and compressed it down to the density it would have at ground level at standard temperature and pressure, then the thickness of that layer of pure ozone would be, if I said 200 Dobson units, that would be 2 millimeters thick. And when we talk about the global average for the ozone layer, what we might discover is that the ozone layer is perhaps a little bit of a misnomer, because the amount of ozone actually contained in the ozone layer has a global average of only about 300 Dobson units. So if you stack 2 pennies on top of each other, that's about the thickness of all of the ozone straight above you in the stratosphere, in the ozone layer. Now, when we talk about ozone holes, what we're talking about is a region where there has been significant ozone depletion. And so there is a lot less ozone present, but again, hole might be a little bit of a misnomer. It's not a place where no ozone exists. It's simply a region in the atmosphere where the ozone concentration has dropped significantly. And normally that means dropping down from about an average of 300 Dobson units down to an average of about 100 Dobson units. So that's approximately the thickness of a dime in terms of the amount of ozone there if you were to compress it to standard temperature and pressure. Now, for comparison, it might be helpful to know, okay, then what would be a Dobson unit for all of the rest of the atmosphere, just for comparison? Well, if we took the rest of the atmosphere and compressed it to the density it would have at standard temperature and pressure, and stacked it, and just put it up, it would occupy a height of about 5 miles, which for reference is about 8 times 10 to the 8th, or 0.8 billion, I guess that would be 800 million Dobson units. That's the rest of the atmosphere. So again, the ozone layer might be a bit of a misnomer here because it really comprises such a very small amount, but it's critically important. The ozone formation and destruction processes that we talked about in chapter 1 that occur naturally are involved in the filtering of UVB light specifically from the atmosphere. And as we'll mention later, when that light's not filtered, that can have serious health effects for those living in affected regions. So let's return to this concept of ozone holes. In the Antarctic survey that the British were doing in the late 1950s, and then NASA has done a lot of these ozone measurements since the late 1970s. So here you're seeing photos that NASA has taken during this time. You can actually go to this site, ozonewatch.gsfc.nasa.gov, and you can see maps of ozone for every single day. They generate a map every single day of ozone at the North Pole and also at the South Pole and at the North Pole. And here we're looking specifically at the South Pole. You'll notice that in 1979 there was the beginning of a hole where we were getting into the blue region. It's getting down into around the 100s, and purple is when we're getting really down into very low measurements. But by 1985, we have a significant hole that has opened up. Now, this is only during a particular time of the year. These pictures are all taken in September. And by 1990, you can see we have a very sizable hole. 1994 is one of the worst years on record with a very low concentration of ozone. I think it gets down to about 92 Dobson units on average. And then in the 2000s, we start to see a little bit of a recovery in the ozone. And as we'll talk about, the question that might immediately come to mind is what's causing this hole? And that's sort of the topic that we'll get to here as we go forward and through the rest of this chapter. So we can look at this data maybe a little bit more quantitatively in terms of this graph shown here. So in red, we have the minimum ozone measurement in September of each of these years, going from 1979 all the way up to 2019. And you can see a fairly sizable decrease from above 200 Dobson units in September down all the way down to here below 100 in 1994. And then we've had some recovery, although it's been slow since then. You can also see in blue just the square mileage, the area that's affected by the ozone hole. Also peaked here somewhere in the 1990s and has maybe slowly been trending backwards since then. So we're heading somewhat in a positive direction. And as I mentioned, this is also not something that occurs all year round. It occurs primarily in the early spring and into the summer of the Southern Hemisphere, which happens to be the months of October through about December. And then we get recovery and closure of this ozone hole as the reactions that cause the depletion of ozone get suppressed. We'll talk about how. And then the atmosphere naturally rebuilds the concentration of ozone, although we never seem to reach quite the levels that we had pre-1979. Now, it's not just the South Pole where the ozone hole appears. In the North Hemisphere, there are occasionally ozone holes that will also appear. There is also depletion of ozone in the Northern Hemisphere. But around the North Pole, you'll notice from these pictures, you may not find anything really striking. Maybe around 2004, there seems to be a slight hole, but there hasn't been the same measure of an ozone hole in the Northern Hemisphere as there has been in the South, although within specific years, there have been some. So if you look in 2011, we'll mention that later, there are some ozone holes that open, but it seems a little bit more erratic. And if we kind of just make a quick comparison here, we see that the minimum ozone concentration in the Northern Hemisphere, that's shown in blue, really has remained pretty constant over the past 30 years, unlike that in the Southern Hemisphere. And if we compare just kind of on a monthly cycle throughout the year, we can see that both the northern and southern hemispheres experience this loss of ozone in the later months of the year, but it's not nearly as significant in the northern hemisphere as it is in the southern hemisphere. And this might lead you to question, so why, if we have a, first off, why do we have an ozone hole around the South Pole and not just around the equator or around the North Pole? And then second, why do we have an ozone hole around one pole, but less of an ozone hole, if any at all, around the North Pole? And those are questions that we will answer in the next video when we talk about some of the specific reactions and conditions that are required for this ozone hole formation.